All right, so we need to go over our notes for section 3 of chapter 12. This section's on concentrations of solutions. You can see your objectives are as given. Given the mass of solute and volume of a solvent, calculate the concentration of a solution. Given the concentration of a solution, determine the amount of solute in a given amount of solution. And then, given the concentration of a solution, determine the amount of solution that contains a given amount of solute. Right? That stuff doesn't necessarily make sense until you see the equations that we're going to use. So we'll get to those. All right, so first off, concentration is just to measure the amount of solute in a given amount of solvent. How much stuff do you have dissolved in your solvent? Remember, from even in biology, I always used this symbol for concentration. I put a C in brackets, so I'm still going to use that, in some cases. But now we're going to have actual units for concentration as well. So you're probably going to see this or this in a lot of cases too, right? A capital M is going to be your molarity. Lowercase m is going to be your molality. And those things are different. They look similar and they seem similar, but they actually are very different. I'm going to show you a demo tomorrow so that you can tell the difference really between molar and molal concentrations. But for right now, we just need to see the equations and know how to work with these things. So molarity, as it says here, is the moles of solute per liter of solution. So you're going to want an equation to go with that. So a big M, molarity, is going to be equal to moles divided by liters. That's your equation for molarity. Molality, though, is moles of solute per kilogram of solvent. So it's similar, but it's actually technically different. So you're going to have a little m that's equal to moles divided by kilogram. Now, if you remember correctly, if that solution happens to be an aqueous solution, your solvent, that water, right, has a density of 1 gram per milliliter. So basically, a liter and a kilogram are the same thing when you're talking about water, which is why these two concentrations seem to be pretty similar, but the way that you actually make them is different. So, like I said, I'll go through a demo so that you can see how that works. You can also look in your book to see how that works. But for today, we're just kind of working through some different problems using these equations for molarity and molality, just to see if we can come up with some answers. All right, so first off, what is a mole? We got moles per liter, we got moles per kilogram for molarity and molality respectively. Remember that a mole is 6.022 times 10 to the 23rd of anything, right? In context of solutions, right, a mole of your solute is going to be a lot of stuff, right? It's going to be 6.022 times 10 to the 23rd of those given particles, atoms, whatever they happen to be. Right, so one of the concepts that we have to jump back to from last year is molar mass, because I need to know how much of whatever my solute is present. I need to measure that so I know how many moles of that stuff is there. So we need to use a molar mass to get from grams to moles and back from moles to grams. So finding the molar mass for sodium hydroxide, because we're going to use it for some examples. It should be something you can do already. All you have to do is look up those values on the periodic table. Sodium has that average atomic mass of 22.99, oxygen is 16, and hydrogen is 1.01. So you add those things up, and that gives you your molar mass, right? If I add these up, I end up getting sorry, I'm using my calculator here and I'm messing things up. And just making sure. I was pretty sure this was the correct answer, but you get 40 grams. I remember I'd have that much precision. My 16 was really a 16.00. I'm just too lazy to write that down. But it'd be 40 grams per mole. Right, and I'm going to use that as a conversion to get from grams to moles and or moles to grams. So you need to know how to do that. We're going to pretty much have to find a molar mass for all of our solute things that we're going to use for all of our examples. So you need to know how to do that. Should be easy enough. Just use your periodic table and add all the pieces up. Okay, this question is something that we'll cover tomorrow, because again, we kind of need to understand the difference between making a molar solution and a molar solution. So we'll just wait on that. And we'll jump right into these examples on the back of your notes. So this first question starts out by telling you you have 3.5 liters of solution that contain 90 grams of sodium chloride. What is the molarity of the solution? Right, so I know I want a molarity, which means that I'm going to ultimately use this equation here. And in order to find the molarity, I better figure out how many moles there are so I can divide by my liters of solution. So I have this value over here of 90 grams, but that's not actually useful right now. I need that to be a mole value. So again, I need to find a molar mass. So sodium chloride, I remember it's 22.99 again, plus whatever my value for chlorine is, which happens to be 35.45. So I'm going to get a molar mass for the sodium chloride that's 58.44 grams per mole. And I got to use that to figure out how many moles of that stuff I happen to have right now. So with this 90 grams, dividing by 58.44 grams, so I can figure out how many moles I have. All I have to do is divide here. 90 divided by 58.44 is going to give me that 1.54 as an answer. I rounded that to 3 sig figs because I'm just following rules that we know already. My unit is moles right now. And so now I do have all the things that I need to complete my equation over here. All I have to do is take this 1.54 moles of my solute and divide it by my total volume of my solution, which is 3.5 liters. And that should give me my molarity. So 1.54 divided by 3.50 equals 0.44, and that's what my calculator spits out, but I'm going to need 3 sig figs, so make sure you add that 0 on the end. So I'm going to have 0.440 as my molarity, right? And I'll just use that big M to label, so that should be my answer. So again, it's not really that hard of a process. You just need to get all the things that you need. I'd start out with your molarity equation, figure out what you need. I had grams, I want moles, so change grams into moles. but then I could just divide and get my answer. So that's one example of molarity. Here's another one, right? Again, you're going to want to recognize that capital M as being your molarity. So I'm going to use the same equation again. But this time it's actually asking me what volume of a 6 molar solution of potassium chromate is needed for a reaction that requires 23.4 grams of that potassium chromate. So this time, instead of trying to solve for molarity, they gave me the molarity already. So I'm going to have to look for the volume instead, which means I'm solving for this variable. All right. So I'll plug everything else in that I know. I don't have a mole value again. I'm going to have to change grams into moles. So I'm going to have to go through the same process I just did on the last slide. 23.4 grams. I need to know how many grams there are in a mole of potassium chromate. Make sure that when you're doing this, there are 2 potassiums there, so do your 2 times the 39.10. And then add a chromium, 52. And then add 4 oxygens, 4 times 16. And I get this value here, 194.2 grams per mole. So I'll divide 23.4 divided by 194.2 gives me 0.120 moles using significance. Again, should have 3 sig figs because the 23.4 had 3 sig figs. And then I plug in what I know into my equation over here and just solve for whatever I need to solve for. So I have this 6.0 molar value is going to be equal to 0.120 moles divided by a certain volume here that I don't actually know. So I need to solve for that variable. You can make that your x. And remember, you're going to have to kind of move things around. That x can't be on the bottom when you solve for your equation. If you want to, you guys can do what some of us like to do from your math class. Put that 6/1 and then use the fish method. I don't care how you solve for it. Just make sure you get an answer for x. Ultimately, you're going to take that 0.120 and you're going to divide it by 6. And it's going to give you an answer of 0.02. Remember, I'm going to need at least 2 sig figs since that 6.0 has 2 sig figs, so I'll throw a 0 on the end of that. But my answer here is 0.020 liters. That's the volume of the solution that I would need so that I would have at least 23.4 grams of that potassium chromate to react. And I could also have more than that volume according to context of this question, but I need at least that much. Okay, so that one was a little harder because I had to solve for a different variable aside from the molarity itself, but it's still doable. Okay, the next question here. A solution was prepared by dissolving 17.1 grams of sucrose in 125 grams of water. Find the molal concentration of this solution. So I have to recognize first that this is that other equation. I'm going to use the lowercase m is going to be equal to a mole value divided by that kilogram of your solvent. So I have a couple things to do here. I don't have anything the way I want it to be. Right? First I have to change 17.1 grams of sucrose into moles, because that's my solute. So then I'll have to know what the molar mass for sucrose is. Shouldn't take too long. 12 times 12.01 plus 20.20 for my hydrogens plus 11 times 16. So I have 340.32 grams per mole. So I'll just divide here and get an answer. 17.1 divided by 340.32 gives me 0.05. I need 3 sig figs, so 0.2 moles. And then I need to know how many kilograms of solvent I have, which is actually really easy to do. You just have 125 grams right now, just change that into kilograms, so move the decimal 3 times to the left. So I'm good now. I just need to take 0.0502 and I'm going to divide that by my 0.125. Again, that's moles per kilogram. And I'm going to get an answer of 0.4. I need 3 sig figs again, so 402 molal. Right, use a little m for molality. It's a big M for molarity. If you can't tell the difference between your capital and lowercase, put a special mark with your lowercase, underline it or something, whatever. I have to see the difference, so make sure that your big M's and your little m's don't look the same. I know mine are slightly pointier when it's the capital M, so I can tell the difference. So that's how you find molality. You take moles divided by kilograms. On any of these, you might want to be checking my work because I could have screwed something up, but you can see the basics of the process regardless. Okay, like my last question here. How much iodine must be added to 100 grams of carbon tetrachloride to prepare a 0.480 molal solution? Again, little m means this equation. So you got to plug things in appropriately. Right? It asks how much iodine needs to be added to 100 grams of carbon tetrachloride to prepare a 0.480 molal solution. My carbon tetrachloride in this case is going to be my solvent, right? Not all solutions are aqueous, remember. So this one, it's different stuff, but I can still figure out how many kilograms there are. Again, just move the decimal a few times. So I know it's going to be 0.1, right, with 4 sig figs, kilograms. I just need to know how many moles of iodine must be added. And that's going to be my variable. That's what I don't know. But it should be equal to that 0.480, little m, for molal. And all I have to do is solve for my variable, right? In this case, the x is on top, so I don't have to move things around. I don't have to mess with this. All I have to do is multiply that 0.1 over. So if I take 0.48 times 0.1, that's going to give me 0.048. And then I'll throw that 0 on the end to make sure that it still has 3 sig figs, like it needs to have 3 sig figs. But that's how many moles of that iodine I need. And because this question is not exactly very specific, that might be all I need, right? That is an amount of iodine. If I was specifically asking for grams of iodine, you just multiply by that molar mass, and iodine for one of them is 126.90. So two of them is going to be 253.8. That's how many grams there are in a mole. So if you did happen to need grams as an answer, you can come up with it pretty easily. So 0.048 times 253.8 is going to be equal to 12.2 grams of iodine. So again, considering I wasn't very specific with this question, maybe you could have just stopped with the moles. But I still want you to know how to change moles into grams. So I just went ahead and finished that off. But now that you have your examples in your notes, you should be able to work with those and finish the worksheet you have for class today. So good luck with that.